Hello. In this video, I'm going to derive continuity equation from Schrodinger relativistic wave equation. So I'll show you the first how to derive the Schrodinger wave equation. Later, we're going to discuss continuity equation from the Klein-Gordon equation. How to derive the continuity equation from the Klein-Gordon equation, and some important points are there. We'll discuss later. So you should start with the relativistic energy equation, that is E square is equal to P square C square plus M naught square C power 4. Then try to substitute replace the energy operator and momentum operator. Energy operator is equal to H cross d by dt, momentum operator minus H cross d by dx. You will get the Schrodinger relativistic wave equation. This is a Schrodinger relativistic wave equation. So here we are going to derive the continuity equation from this Schrodinger relativistic wave equation. First, we need to write Schrodinger relativistic wave equation, that is equation number 1. Then make this equation as complex conjugate. So complex conjugate of this equation is minus h cross square dou square psi complex divided by dou t square equal to minus h cross square c square del square psi complex plus m naught square c power 4 psi complex. This is the complex conjugate of Klein-Gordon wave equation. Then here I am going to multiply the left side of the equation number 1 by the complex conjugate of wave function, and the left side of equation by the complex wave function psi into the equation number 2. So first I'm going to multiply left side of the equation from equation number 1, this equation, which means, okay, so this is the equation. From this equation I'm going to multiply the left side by complex conjugate wave function. I got this equation. And one more step, second step, you need to follow this one. This is the second step. So we should multiply wave function from the left side of this equation. Then you will get equation number 3, you get equation number 4. From equation number 1, I got equation number 3. From equation number 2, if you multiply equation number 2 by wave function psi, you will get equation number 4. These are the basic steps, first 2 steps to solve the continuity equation from relativistic Schrodinger wave equation. Second step is we need to subtract one equation to other equation. So here I'm going to subtract equation number 4 minus equation number 3. Subtract, here minus is there, right? Minus get plus. This is equation number 4. Equation number 4 term. Here already minus is there. Minus into minus plus h cross square psi square dou square psi divided by dou t square equal to we'll get cancel these two terms, right? The remaining term is this one, minus h cross square c square psi del square psi complex minus to minus plus h cross square c square psi complex del square psi. These two terms are going to cancel each other. So this is the equation. Next step is try to simplify this equation by observing carefully. Here the terms are there, different terms are there. So I'm going to cancel this h cross square term. The remaining terms are here like this. Just I'm rearranging this equation. Okay, first I'm going to write this term, second this term here. Okay, then c square is there here. Here also c square is there. C square get common. So then we'll get this bracket term equation. If you observe this equation carefully, dou divided by dou t, time coordinate term is there. Okay, and here the space coordinate terms are there. So what we are going to observe here carefully, two terms are there. One is the space coordinate term and the term is the time coordinate term is there. Now multiply this equation number 5 equation by IH cross divided by 2m, you will get this equation. Okay, so if you observe carefully this equation here, it is look like the continuity equation. So we know the continuity equation general term is dou by dou t rho probability density into the current density Z is equal to 0. So this is the continuity equation, general continuity equation term. So here I'm going to write this equation as a continuity equation form. So in this term, this is the first term, the probability density term, and this one is J term, the current density term. So this is the way to derive the continuity equation from the relativistic equation. So we should follow the same step to derive the continuity equation from Dirac relativistic equation also. So if you follow these 4 steps, you will get the continuity equation from the both the Dirac relativistic equation and Schrodinger's relativistic equation. You will get the continuity equation. So we'll discuss some key important points here. The first one, this is the final one. We got the continuity equation, right? Here the terms are there, two terms. One is the probability density term. The P is the current density term. J is there. Okay. So here I'm going to discuss these two terms very carefully. Here we have to define the position probability density by equation number 7 and the probability current density by equation number 8. This expression for J r comma t is identical with the one in non-relativistic case. So however, the expression for probability density P r comma t is completely different from the one we observed in the non-relativistic case. So we already discussed this non-relativistic case also. It is there in playlist, I think, mathematical physics, mathematical quantum mechanics, maybe lecture number, class number 21, 24. Okay, so just go and watch 24 video, so you will get idea what is a non-relativistic case continuity equation. Okay, now we are going to investigate equation number 7 because this term is a probability dense term is quite different from the general equation term. This is the general equation term. So almost current density is same. Current, current density equation term is same, but a different term we observed here. This, okay, probability density term. So here I'm going to give one information here. In case here the wave function psi is real, if you consider this equation, this is the probability equation, right? This is the probability current density equation. If we consider wave function psi is real, so I understand this equation like this. For example, if I take psi, wave function psi is real, right? I'm going to give one real number 5. So what will happen this term here? If you place the wave functions, in place of wave function, the real number 5, then this term is going to be vanish. When psi is complex case, so it's better to write here the wave function psi will going to the vanish, this term vanish. If psi is complex, if you consider this wave function psi is complex, for example psi equal to minus I 5, what is the complex conjugate of this function is plus I 5. So we'll get the different form of equation here. So I try to substitute here this equation, simply the same equation here. I'm going to repeat this one. So if you put in place of wave function complex conjugate function, we'll get this type of equation. Therefore we can write this equation like this: modulus of psi star square, where this P of r comma t is positive when E is positive, and negative if probability is the positive. So E is a positive case only, right? If probability is negative, then energy is also the negative case only. In other words, the probability density takes both positive and negative values. Hence, the P of r comma t given by equation number 7 cannot be regarded as the position probability density. Right. So, due to this reason, the Klein-Gordon equation was the first uh, discovered. This dilemma was solved by the Pauli and Weiss in 1934. So it's going to break the position probability density rule, right? So probability we can't get both negative and positive. So either we'll get the only one values, right? We can't get two values, right? This dilemma was solved by the Pauli and Weiss in 1934. They interpreted EP as the electrical charge density, EJ as corresponding electrical current density. This is reasonable was charges can take place both positive and negative values. If the system has the single particle of a given charge, P cannot have the different signs at different points. That means the theory is useful only to systems of particles having both signs of charges. With this reinterpretation, it is considered as the relativistic wave equation for the systems of arbitrary number of particles and then the anti-particle systems. So this is the explanation. It is given by the both Pauli and Weiss in 1934. This very important information from the continuity equation.